So in this situation, I've got a vertical circular motion. Previously, we've been looking at stuff that's horizontal. This is a vertical loop. And I want to set up a reference frame first, because Lillian was asking about reference frames, and we should have that in there. For this one, I think just to be difficult and just to ruffle feathers, I'm going to make down be positive and make up be negative. Just to be difficult. Not very difficult. And so this is a gymnast that's somehow at the end of a rope. Somebody in the past said, is this like Tarzan? So I threw it in there. Does anybody even know who Tarzan is anymore? Some fella who grew up in the jungle. I don't really understand the backstory. But anyway, swings on ropes. That's the important thing here. So we got a gymnast, though, that's swinging on the equipment. And want to think about what happens at the top versus the bottom. For argument's sake, let's just make it be one rope. And somebody will say, like, gymnasts don't usually swing on one rope, and they don't usually do full circles. Well, neither does Tarzan, so, like, give me a break, all right? So we're swinging vertically, and if you really need this to be realistic, maybe this is your arm swinging a bucket of sand at the beach, and we're talking about the tension in your arm. But I'm going to be talking about gymnasts. So I got this gymnast up at the top. And up at the top, I say the forces acting on the gymnast would be the force due to gravity. And if they are holding on to a single rope with their arm, this is their mass, there would also be a tension acting down on them when they're up at the top. When they're at the bottom, force due to gravity is definitely acting down on them. What direction is tension acting? What's that? Up. All right, Evie says up. Now, I'm actually making the FT be bigger on the bottom than it is on the top. I'm doing that on purpose because although I haven't been a gymnast before, I have gone to the beach with my kids and I have filled up a bucket of water and I've done the old swing the bucket of water above your head thing. How many people have done the swing the bucket of water above your head thing? Yeah? So you're at the beach wearing your best bathing suit, and you've got a bucket of water above your head, and you swing it around in a circle. And if you were just to hold the bucket up above your head like that, the water would dump down on your head. But that's not what you're doing. You're swinging the bucket around in circles so that sometimes it's at the top and sometimes it's at the bottom. And everybody's really impressed because when it's at the top, no water comes out, right? And people have this idea of centripetal force being a thing. Now, when you feel the centripetal force, when you feel the effects of this, really what you're feeling is the tension in your arm, right? The centripetal force, like we said before, is the net force. And so what we should really do is say, that diagram there, the tension force isn't the centripetal force. Tension force plus Fg is the centripetal force. So while we've maybe experienced this, we might have done a little bit of a misread on it. If we were thinking in our mind centripetal force, we might not have realized that the tension in our arms isn't actually the centripetal force. It's the cumulative Fg and Ft that's the centripetal force, okay? And likewise, at the bottom, it's the cumulative Ft and Fg, but I also know that at the top, I feel less tension in my arm than at the bottom. And if you've never done this, live a little. Go to the beach, you know, it's still warm, fill a bucket with water, swing it above your head, and just like whoop it up, you know? But you're gonna feel these effects. James.
It's like the water in the bucket is there a force that's opposing the force of tension?
So if the bucket in the water is moving around in a circle, is there something that's acting on the water?
No, is there something that's like going the opposite direction of Ft?
Oh, so like is there a force that's going upwards?
Yeah.
No, so that's the thing. I made a point earlier that centripetal, I'll write it, centripetal force points towards the center of motion. This Fc here points towards the center. That way. And there's likewise an Fc down here that points that way, towards the center of curvature. If I think about the water or the gymnast, there is no actual force that's pushing upwards on this gymnast or on the bucket of water. What's keeping the water in the bucket, example, is inertia. At any given moment, that water wants to keep on going off tangentially, and that inertia, as I swing it into the position where it's here, keeps that water constantly wanting to go like in a direction that presses it up against the bottom of the bucket. So it's that and that's due to what we call the centrifuge effect, and that's not to be confused with centripetal force. And tons of people get it mixed up because they both have to do with going in circles. Okay, but this one's an inertial reality, whereas this one is a true like net force reality. Okay, and it's hard to recognize the difference, and we can still talk about that more if we want to later conversationally. So in this one, I've got Ag equals 9.81 meters per second squared, and I'm going to make up some numbers. I'm going to say that this gymnast can move around at 5.00 meters per second. And just to make it easier, I'm going to say that that's how fast they go at all points. Anyone who's a gymnast knows you actually go a little slower at the top than you do at the bottom. Anybody who has swung water above their heads knows that the water goes a little bit slower at the top than it does at the bottom because of conservation of energy. But we're going to fudge that a little bit just to make things easier for conversation today, okay? And then the diameter. The diameter of the circle or circular path, D, is equal to 2.40 meters. And if you're ever given a diameter for these kinds of problems, immediately calculate the radius because you'll forget if you don't. So I'm going to do that right now. So I mentioned it just so that I can undo it because we're all going to forget at some point. And then the mass of this gymnast, again, just to have a nice round number, 100 kilograms. 100 kilogram gymnast. I know that most gymnasts are not 100 kilograms. This is just a nice round number to deal with, okay? All right, so how do we investigate this? How could we figure out the tension? That's the thing that's being asked of us. How could we find the tension in this situation? Well, the tension's actually going to be different at the top and the bottom. I mentioned that. But we got to figure out how we know that. So if I do the FG calculation, I'm not going to do this by generalized equation. I'm going to do this by piecewise calculation because I know there are some people that are doing it that way too. So I'm going to model that way this time. 100 kilograms times 9.81 meters per second squared equals 981 newtons. That's a nice quick calculation. The FC, I've got enough information to calculate this, would be mv squared over r. And so we got our 100 kilograms. People that are generalized equation people, you'll notice that if you try it the generalized equation way, these masses will probably cancel out for you. But I'm doing it the piecewise way to sort of support these different kinds of thinkers. 100 kilograms times 5 meters per second squared divided by 1.20 meter radius. And I'm going to jump straight to the answer on this one. It's 2,083.3 repeated newtons. And that seems fairly straightforward. But I want to look at situation 1. Situation 1 is when I'm at the top of the motion, when the gymnast is upside down, up at the top. And the free body diagram for situation 1 would have an equation that would say, all right, well, FC is equal to FT plus FG. If I isolate for FT, FT is equal to FC minus FG. Notice that I did not insert necessarily negative signs. I didn't even think about negative signs based on the reference frame. I'm just making an equation, okay? And so I get my FT all by itself. In this case, FG is down. But FC, I'm going to write question mark because at the top, isn't the FC downward? But at the bottom, the FC is upward, right? So I'm putting question mark there just to remind myself that I might forget. Okay, so I don't want to apply positives or negatives to that yet because in situation 2, FC is going to be up, right? So I say, all right, well, FC minus FG. FC was that 2,083.3 repeated newtons, and right now it's downward. So it gets to be positive because we declared down to be positive. I'll bring that picture back in screen. I'm having a hard time keeping it all together at the same time. Maybe I'll zoom out. Okay. Minus the FG, so minus 981 newtons. And somebody who's quick on the calculator, tell me, do I have this right? Can I trust myself from the past? Is that the tension force? Oh, on screen, sorry. Is that the tension force? Yeah? All right. And I know I could round this off to 3 sig figs, it looks like. So, I don't know, kind of annoyingly, 1.10 times 10 to the power of 3 newtons. So therefore, the tension force is 1.10 times 10 to the power of 3 newtons at the top. Okay? Notice that I'm not even bothering with direction because the tension force is a magnitude. How taut is the rope? That's the tension force. How tight is it? Okay? In situation 2, if I wanted to find the tension force at the bottom, I'd start actually with the same equation, Fc equals Ft plus Fg. And I got to decide, do I want to sub in the negative sign at this stage when I'm designing my equation? Or do I want to sub in the negative sign when I sub in my values? How many people want to sub it in at the equation stage? Vote for it. Who wants it? How many people want to sub it in when I sub in my values? All right, we'll sub it in when we sub in our values. By democracy. So let's get Ft all by itself. If we get Ft all by itself, we actually end up with the exact same equation as the one before. Fc minus Fg. When I sub in my values, the Fc hasn't changed because it's going at the same speed at the bottom, so 2083.3 repeated newtons. However, at the bottom, what direction is Fc pointing at? Upwards. So when I sub it in, you guys voted to put the negative sign in when the value comes in. It's got to come in now because it's going upwards now. Okay? Minus Fg. Fg was 981 newtons. It's still down. Down is still positive. And this time I get 3064.3 repeated newtons. Somebody with their calculator. Did I get it right? Okay. And again, we can round it off to sig figs. 3.06 times 10 to the power of 3 newtons. And we can have a therefore statement. Therefore, the tension is 3.06 times 10 to the power of 3 newtons. Oops. At the bottom. And this whole prediction of the tension being higher at the bottom comes true. In fact, it's like almost 3 times the tension at the bottom, right? There's this other thing over here. It's a silly little cartoon, and I feel like the cartoons didn't translate very well. Like the resolution isn't great. But there's these little characters, these little bugs. And these little bugs live inside of an inner tube. And the inner tube that they live in, actually, they're characters from Sesame Street. But these little bugs live inside of they're called the twiddle bugs. You can look them up if you like to. They're very cute. They have YouTube videos and stuff and everything. But if you ever look up the twiddle bugs, they could live inside of this inner tube. And if the wheel was spinning, you can imagine this. If this wheel could go at just the right speed, can you imagine that these little twiddle bugs would live on the inner hub of that wheel, and there could be a centripetal force such that there could be a normal force acting on them. They would be exactly equal to force due to gravity. And then when you take that silly situation and you take it to the next level, you can imagine how a centripetal force scenario like this could be used to simulate gravity in a space station. So if you had a giant wheel like this and it wasn't twiddle bugs inside of a bicycle wheel, it was humans inside of a spinning space station, you could spin it at just the right speed so that the centripetal force would create a normal force equal to Fg. And then this would allow people to walk around the outer hub of this wheel. Now the thing is, would it be the same value if you put a platform at a smaller radius? No, because remember, Fc is equal to mv squared over r, right? So smaller radius wheels, if we make this space station, we could say, hey, if this was a space station, forget about the twiddle bugs. You could say that if this was a multi-story space station, this is what a multi-story space station would look like. People that are at this space station, this whole thing might spin at just the right speed so that people at this level of the space station would have a normal force. caused by FC that was equal to FG. And they could walk around and they maybe would have less muscle atrophy, you know? People out here, because the radius is bigger, wouldn't the centripetal force be bigger? And if you really wanted to exercise, maybe you'd go out to this space station. Or maybe that's the layer where you keep your water or something like that. Can you imagine? Or maybe that's where you'd keep your human waste, because that's where you'd want to just send it. It would go there naturally because of centrifuge effects. Maybe you want to keep all your heavy equipment at the inner layer because it's going to spin and make the heavy equipment easier to lift because the normal force would be less. And that could be a design thing. Now, I'm not planning to design a space station, and people say, well, does it really have to be like a wheel? Could you make a space station that takes that idea and actually makes it a cylinder? So that you actually have a cylindrical field. Can you imagine? Like a soccer field that is a radius away from the radius of rotation, but it's a soccer field that wraps around on itself. Could you do that? Could you even set up a lighting system at the center, some sort of nuclear fusion core, you know, strip lighting, but on a big scale that lights up that field? Could you grow crops there? That's the world of sci-fi, right? But it's kind of a neat thing. And if you get into sci-fi and you see cylindrical interstellar spaceships or something like that, this grade 12 idea is the kind of thing that these people ran with. And it's kind of a neat idea for us to think about. More immediately, we might think about International Space Station type stuff and having this kind of a thing be like a reality in our local vicinity for space research. Hey, but if we ever wanted to do long-term journeys, maybe having fields with center of axis lighting systems for growing crops, maybe that could be the thing, you know? Anyway, something to think about. Roller coasters on a less grand scale. So roller coasters have this other idea that might involve normal forces as opposed to tension. And when you're at the top of a roller coaster, look at these people riding the roller coaster. When you're at the top of the roller coaster, hey, I'll change my reference frame. Last time I made down be, actually no, let's just be difficult again. Let's make down be positive again. If you let down be positive again, and up be negative again, we can set up another free body diagram situation where I know that on my sketch, I would have FG acting down on this person and F normal acting up on this person. This person, when they're at the top of the loop, upside down, F normal is acting down. What direction is FG? Down also, right? So FG. And so if I were gonna clean this up a little bit, maybe I have a mass of 141.5 kilograms for the person in the car. And I know that's not really a round number, but that's okay. And you gotta accommodate all kinds of random masses on these rides. Speed of 100 meters per second. Oh my gosh, that's fast. You ever been on the Leviathan? That thing will kill you. 37.0 meters for the radius of curvature. Notice that's the radius, not the diameter this time. And I know that at the bottom, the FC would be up, and at the top, the FC would be down. So when I draw my free body diagrams for this, I'll start with scenario 1. That's when you're at the top. F normal is down, FG is down, and then not attached to the free body diagram, separate, FC is down. Scenario 2, I would have FG down, F normal pressing up on my bum. Notice F normal is pressing down on my bum in the first one because I'm at the top, I'm upside down, so normal force is pushing down on my bum because I'm upside down. And that's equal to FC. Again, notice that I don't attach FC to the diagram, and then FC is pointing upwards in this case. So I have my reference frame, I have my free body diagrams, and I would have my equations. FC is equal to F normal plus FG. This guy over here, FC is equal to F normal plus FG. I want to insert my negative signs beforehand this time. Notice that all the forces are down. I called down positive. In this one, normal is up. It's negative. Centripetal force is up. It's negative. I've inserted my negative signs into my equation this time. And so when I go to isolate for my F normal, I would get F normal equals FC minus FG. For this guy, I would get F normal equals FC plus FG, mv squared over r minus mag, mv squared over r plus mag, and we can sub in our values. Now, in the interest of time, I'm going to let you guys work this out. But I'm going to tell you right now, the answer, you sub it in, check to make sure, 3.96 times 10 to the power of 4 after sig fig rounding, and 3.69 times 10 to the power of 4 newtons after sig fig rounding. I know they look similar, but it's 6.9 and 9.6, okay? How fast should the coaster be moving so that the rider feels no pressure on their bottom? Well, that would be a situation where I'm at the top of my loop. Remember, F normal, Fg. Remember the equation is F normal equals mv squared over r minus mag. I just did that up above right here at the top of the loop. But if you want to feel no normal force, that guy would zero out. And essentially, I could bring that mag back over to the other side and say mag would be equal to mv squared over r. Notice that the masses cancel out. And if I want to know how fast, I'm finding v. So I would say v squared equals agr, or v is equal to the square root of agr. And again, the cute thing about this is if you want to give somebody a real thrill at an amusement park, a real thrill happens when you don't feel any pressure on your bum when you take the loop, you know? Because you feel like you're about to fall. And what a thrill that is. And the cool thing about that is it's mass independent. So it can be a thrill for all riders. Notice it doesn't matter. Big or small, I go on there with my kids, I'm way bigger than my daughter. My youngest is a fraction of me. And we're all screaming at the same time. That's nice, right? So I'm trying to tie this stuff to engineering that people might want to do, whether it's amusement parks or roads. You guys can plug in the numbers. The answer does end up being 19.05 meters per second based on our givens though, okay?